information here is really critical. If you don't have your if you don't have the equation for your polynomial, let's say I just give you a graph and I say, because this is a quiz or a test question that I use a lot, okay? Could we put the schedules away, please? And I'll explain those in a little bit. Thanks. So one of my favorite questions to ask you on a test or a quiz is to give you a graph and say, what's the minimum degree for this particular graph? What's the minimum degree, okay, of the polynomial? So first of all, you have to determine, is it going to be an odd or an even degree? And we just look at the end behavior. If your arms are in different directions, you know it's odd. If they're going in the same direction, you know it's even. So right away when we look at this graph, suppose we didn't have this equation here, we know it's an odd degree. It says the graph will have at most n-1 turning points. Those are your relative maxes and mins. You can see here that I have 2 relative maxes and mins. So if you set that equal to n-1, you solve for n and you get n is 3. So this tells you that the smallest degree polynomial that could give you a picture like this would be a 3rd degree. It may be a 5th, it may be a 7th, but the smallest degree is 3. It has at most n real zeros, excuse me. If you go to your graph, you can see that at 3 different points here, you have zeros. They all occur once, so the power on the factor, when you factor this, will be 1. And so it has exactly the same number of zeros as the degree in this case. Now you might say, well, when would there be an example where I wouldn't have, say, the same number of zeros? We'll get to that later. If you think about any parabola that's been, say, vertically shifted up, like x squared plus 1, that doesn't have any real zeros, but it has 2 zeros. They're complex, and that's where we're going on Friday. Okay, so let's apply this knowledge to these. There's so much in this little exercise that I can't make sure you got it all, but when you approach something like this, a good way to start, like if you see something like this again on a quiz or a test, is to just identify the degree. Is it even or odd? So if I look at these pictures, the first thing I do is even degree. What's this one, B? Odd. Could you shut the door for me? Odd degree. Thank you. C, what about C? Odd because the arms are going in different direction. D, even, right? This is how I start. And E is totally odd. And the last one is even. Then I think about my leading coefficient. If my right arm is up, as it is in B, D, E, and F, I know my leading coefficient is positive. So right away, I've got some information before I even start to try to pick out my equations. Okay. The other thing that and Alan was pointing this out to his group, this is the only parabola here, and you only have one quadratic function right here. So if you factor this, first of all, if you put it in decreasing order like this, and you factor it, it looks like this. It says you have a 0 located at 1, 0. That's the x-intercept. And it has a multiplicity of 2. So it's going to look like it's going to bounce right at 1, 0. It's going to be coming down. And then it's going to bounce right back up. Okay. So that eliminates that one right away. The other thing I was pointing out to various groups, I didn't get around to everybody, but every time you see something like this, I should use a darker color. When you have an x-intercept or a 0, and it looks like a little parabola like this, that tells you something. That tells you that in your factorization of your polynomial, x occurs twice because it has a multiplicity. This has like it bounces here at 0. So you have x minus 0 twice, which is the same as x squared. So what that means is that for the equations, like here, x squared is a common factor. X squared is a common factor. X squared is a common factor. So when you see that shape at the origin, you should look for a polynomial that has x squared as a common factor in it. This is like all the bits and pieces of information to try to put it together. Now, you may not be there yet, but I'm just trying to help you learn how to think about some of these. Now, the other thing, folks, is if you had trouble with some of this, is I would really encourage you to go back and try to apply some of this stuff and try to synthesize it. Any questions before I move along? Okay, I want to tell you a little bit about the schedule. For those people who handed in the survey, I really appreciate you taking the time to do that. Some of the comments I got were, the one that I saw most frequently is some people said they wish they had a review. Now, I haven't done a review in Math 107 before tests for a long time. However, I said I asked for feedback, so I'm going to act on it. So if you look at your schedule, what you'll notice is that, and please replace your old schedule, is that I've taken out, I'm not going to have any classes devoted to quizzes, that your final 2 quizzes, it's right here, Fabian and Dean, your final 2 quizzes are both going to be take home, which will free up a class. And if you notice that on May 4th, I'm giving you a review before the 3rd test. Okay? Do you have one of these, Giovanni? So I took the comments to heart, and I've reinstituted a review for the last test, and the quizzes are both going to be take home. So I hope that helps some of you. So let's move on to today's material. Yep, Clay? It will just be like 1 and 2. The quizzes are always due the very next class. No, no, you have to be in class to get it. It gets lost? If you lose it, if you're here and you pick it up and you lose it between class and the next class, you can email me and I'll send you a copy. Okay? Yep. Originally, the preview exercises for today only looked like this, but I put that last class activity in because I knew you wouldn't have time on Monday to get to it. Today, we're going to talk about polynomial regression. We've already done polynomial regression. It was just called linear regression. But now we're going to move up. What if we have scatter plots that a straight line wouldn't be a good model for? What are our other choices? So that's what we're going to look at today. So here's a scatter plot. If you were going to use some of the information that you've just put together with some of your polynomial functions and looking at their graphs, what degree polynomial might you choose? So if you could just write your idea down right now at your seats. What polynomial, what degree polynomial? Write it down on your own paper. I'm not going to come around and look. And when everybody at your table has talked about it quickly, put up your flag. Okay. So what did tables come up with for a degree? Did everybody come up with 4th degree as a possible model? Okay, 4th degree. And would one person like to explain why they came up with a 4th degree? 3 turning points. Yeah, so if I had a model, we'd see that we would be, these points are decreasing, but then they increase, and then they decrease, and then they turn around again and go that way. So you have 1, 2, 3 relative maxima or turning points. And we know that n minus 1 equals 3 is the most number of turning points we can have at most. And if we solve this for n, this would have the minimum degree this could be would be a 4th degree. So if we're looking at our graphing calculators and we're trying to do a regression, Remember, we go to stat, we go to calc. A fourth degree is called quad. No, not quad, because quad is second degree. And that's always an interesting question if people like to look back at things. Well, why is quadratic second degree? When I was at UMass, I lived in there was something called the quad, right? And that's because had 4 buildings along the side of it. So why is it quad for quadratic? That's kind of an interesting question. But anyway, for a regression that you do for a fourth degree, you would use 7, which is called quartic. So a fourth degree polynomial is a quartic polynomial. So you would go down to number 7 on your calculator and do a quartic regression. Okay. So let's kind of review some of the steps for these regression equations. And here's some data that I found a while ago, I think last year, which I thought was kind of interesting. In fact, I just asked last night before I left, around 6 o'clock, I asked the evening librarian if she could get me any data on what's happening to women in full-time civilian labor force, the women in the full-time civilian labor force with children under the age of 6, if she could find me any data after the year 2000, because we're up to 2015 already. And I had looked around in the Bureau of Labor Statistics, but I couldn't find exactly this table. And she found me 2 articles and some tables. And if you're interested in reading any of that or seeing what's happening, I can send them to you. Just let me know. But because it's curious, whatever model we pick today, what really happens after 2000, we don't know. And so one model is going to lead us in one direction, no pun intended, and another model will lead us in the opposite direction. So let's take a look and review the steps that we do. And some of you will have this older calculator, the TI-83 Plus. And if you've borrowed the newer calculator, it's going to look like this. So I will show you the steps for each calculator today so you know how to enter. Everything is written down on your activities there, your lecture notes. So first of all, the most important thing for entering the data is where are we gonna set a base year? Do we actually put in 1975, 1980? And if you look at this here, we're gonna use T is the number of years since 1970. So what will be the values of T for each of the years that we have here? What's T going to equal in the first case? 1970 would be 0, yeah? So 75 is 5. Just go ahead. 10, 20, 30, okay. Every time I do this, I think back to when I was young playing hide and go seek. 5, 10, 15, 20. No. Anyway, nobody plays outside anymore. Everybody's on their computers and video games. It's kind of sad. Okay, so if you recall, on both of these calculators, to enter your data, you hit the stat button. Okay. Turn it on first, Linda. Okay, hit your stat button. You go over, and the very first thing is to edit your list. So you just stick with that. You want to edit your list. And if you have your calculator handy right now, you could try doing it along with me, or you could just watch, whatever suits your purpose. They're right there on the chair. Okay, so you hit edit, enter. And if you notice on one of these calculators, I already have the data entered, and so I could be right with you time-wise. I left one of them blank. So for L1, that's going to be the year since 1970. I'm just going to enter my data, 5, 10, 15, 20, 25, 30. So that takes me up to the year 2000. Okay? Now I just scoot over, and now I have to put in the number of women in the full-time civilian workforce, and these are in millions. Would someone read it to me? It will be a lot easier than my looking back and forth on the paper. Would someone read it to me? 4 point what? Thank you, Taylor. Yep. Next one. 5.886. Thank you, Dean. 7.322. Yep. 8.732. Yep. 9.587. 9.736. Now you always want to make sure before you go and do any calculations that you have the same number of data values in each column, or else you're going to get an error and it's going to say dimension mismatch. So make sure you didn't skip anything, or you didn't put one extra number somewhere in one of the columns and it doesn't have a partner. You have, for each value in L1, you have a value in L2, a corresponding value in L2. Okay. So this wasn't the hard part of regression, right? You all, most of you remember that you go to these lists and you put in your data. Okay. Now, what you want to do before you even think about what polynomial function you're going to look at, you have to look at the data. You have to get a picture of the data. So you go to your stat plot. Your stat plot is right above your y equals button. And notice it's either yellow or blue. So you either hit second y equals to get to stat plot, or the blue second y equals to get to stat plot, depending on which calculator you have. All right. Now, I want to look at my stat plot. Number one is off right now. So I hit my enter button on both of these, and I just want to turn it off. Turn it on. So I toggle over to on and I hit enter. Okay. And notice what type of stat plot do you want? The very first type that's always highlighted by default is the scatter plot. As you scroll down, you notice this tells you where your data is located, L1 and L2 in both of these. So you're fine. You don't have really any other work to do. But before you graph it, you want it to graph with a certain window. You don't use zoom 6 anymore because that's for y x minimum to be -10 to +10 and y minimum and y maximum -10 to 10. You want a stat plot. It's going to just be the first quadrant. So it's zoom 9. So you hit zoom 9. So everybody hit zoom 9. Zoom is right here. The middle button in the top row, zoom 9 is your stat plot. Zoom 9. Okay. Now, you may have some data from the previous class and stored in Y1 or Y2, so you want to clear that out or else you're going to get some funny looking things on here. So zoom 9, and you should get this stat plot. So I'm going to take this out right now, and of course I don't have my camera on already, so I'm going to lose this camera. I got to call them back up again. This always happens to me. You'd think I'd learn, huh? I haven't learned yet. Okay, so let's get up this first picture and take a little picture of it. It doesn't matter which picture I grab from which calculator. All right, so here's the picture of the data. And if I look at my other calculator and grab the picture, might as well take 2 pictures because we're going to talk about a couple of possible polynomials. All right, so let's just scoot this down here. Okay, so here's, yeah. That's all right, use L2 or L3, it doesn't matter, someone deleted it, I can get it back later. Doesn't matter which list you use. So when they were clearing them, Taylor, instead of hitting clear enter, they hit delete enter, and so they lost the whole list. Okay, so there are our 2 scatter plots. Now part B says we will find the line of best fit and the parabola of best fit. And let's go back and look at our pictures here. Does it make sense that we might use a line for this to try to model this? Does it make sense? Yeah, I mean, you could easily imagine a line getting pretty close to that data, right? It would have positive slope, right? What kind of parabola might you be looking at? What would be the leading coefficient of the parabola? Positive or negative? Negative, because you see that this data is increasing, and it's starting to look like, even though that point's a little bit higher, it may start to level out and perhaps come down like this. We don't know. That's the big question. This one's going to tell you it's going to increase at a constant rate forever and ever. Okay? So how do we get the information for our equation from the calculator? And then how do we determine which one we should use to actually try to predict, say, the number of women in the workforce beyond 2000? Well, I'll wait until you guys. So when we were just looking at linear regression, all we had to do was find the value for R, and that's what you did in your projects that you just handed in today, the correlation coefficient. Little baby R tells us one and only one thing. I want you to understand this before you leave this class. It only talks about the strength of a linear relationship. So if you're looking at a relationship that's different than a straight line, we can't use baby R. So what you can get available for all of your other polynomial regressions is something called R square. Capital R square on anything higher than a linear function, and little baby R square. Those are the values that you compare to say, what is the best model? Okay? You look for a high R square value. So if we go to our linear, if we go here and we now say, I want to perform a linear regression on this, that's located in the stat button. This is all written down, folks, so don't worry. It's all there in your notes. You go over to calc and you say, I want a linear regression. And I also want to point something else out again. Notice you have a linear regression at number 4, just in case and you have a linear regression at 9. The only difference is in number 9, they make A be your intercept, because in statistics, you always start with your starting value, and then you see whether you increase or decrease from there. In an algebra class like we have, notice we're so used to seeing a straight line in the mx plus b or ax plus b. That's why they have two different ones here. So you hit enter. If you have the old calculator like this, you have to say, hey, tell your calculator where you're storing the data. Well, I'm storing it in L1 and L2. Notice above the key 1 and 2, you see a little L1 and a little L2. So you hit second L1, you hit your comma, second L2, and you hit your comma. Now, this is always the part of your regression that you forget. And you have to tell the calculator where to store the equation that you're going to get for your regression. And it takes a couple of steps. You want to put it in one of the equations under the y equals. To do that, you have to tell your calculator, I want to go to the var. You use this key right here. The var stands for variables. I want to put it in the y variable. So you hit vars. You scroll over to the y vars, and it's a function that you're entering, so you just hit enter. And then it's totally up to you whether you pick y1, y2, y3. You could keep all your equations in and just turn them on and off in case you've got to go back and answer some questions about them. So I'm going to pick y1. And there it is. There's everything the calculator needs to know. It knows what data set it's performing the regression on, and it knows where to store the actual equation. So now when you hit enter, you will get the values for A, which in this case is your slope, the value for B, which is your y-intercept. So what is it saying? What does B mean here, the 3.991? What is that telling me in the context of this data? What is that telling me in the context of this story? Yeah, what is the y-intercept telling you here in terms of this story? The number of women full-time in the full-time labor, civilian labor force was what? Right. So this is where we started. That's why I like the statistics model. This is where you start. At 0, you have roughly 3 according to your model, almost 4 million women at 0, which was 1970. This is the number of millions of women in the full-time civilian labor force. Yeah, it means the civilian labor force is non-military, and I don't know how the government is actually categorized. I'd have to check that with the articles I just received. I don't know if government would be, yeah, I think government, I think it just means non-military. Although I don't know how CIA and all those people would be classified. No, that's still civilian. Private companies is still civilian, yeah. Okay, so how would we now put in the equation for the regression line? Remember, your calculator is going to have all this accuracy. It has all of those digits. For reporting purposes for me or for you, you would just say y hat equals, choose 2 or 3 decimal places. It's up to you. I usually look at the data and I'll say I've got millions of people here. So if I cut this off at the tenths, I'm losing hundreds of thousands. My estimate's going to be off by hundreds of thousands. So I usually go for 3 to 4 decimal places. So in this case, I would say 1x plus 3.9919. Okay. Now, the R square value, notice in this case it's a little baby R square because it's just your correlation value squared, is 0.959. That's pretty darn good. For your projects, you only needed an R value of 0.6. So here our R value is almost 0.98. That's a pretty good model. Let's look at the quadratic model, and we'll do that with the other calculator. So the other calculator's got a little different setup right here. So I don't want that big. Come on, just come up here. No, just come straight up. There we go. Sometimes just getting these to, there we go. All right, so we've got our data entered. Okay, we hit stat. Now these calculators are a little different. You don't have to do quite as much work. So when you go over to calc and you go down to your regression model, notice it already has your lists in there, so you don't have to bother remembering how to do that. The only thing you have to do is go down and say, hey, where do you want to store your regression equation? So it's under your y variable, so you hit which button next? To get to y1, which one do you hit? Beside the y equals, you got to store it in there, and we don't have the equation yet. Vars, y vars, enter. Now, we already have them. We don't have the linear equation in y1 because I've switched calculators. So I'm going to use y1 again here. And now I go down to calculate and I hit enter. And there's the data I need, right? I have A and B. Uh-oh, what don't I have? I don't have my big R square. How am I going to compare which one is the most accurate model or the one that fits? What did I forget to do? Does anybody remember? Make sure before you do anything, or else you're going to be, that your diagnostic is on. That should, when you get any calculator, make sure your diagnostic is on. Where's that located? Down above the 0, you see catalog. So you have to hit second catalog. And unfortunately, you can't put a D in or anything. You got to scroll all the way down. It takes like 10 whole seconds or so, depending on how fast you are, to diagnostic on. Whoo, here I go. I'm still not there. Da, da, da. Oh, there it is, on. You have to hit enter twice until you see the word done. So you do enter, enter until you see the word done. And if you hadn't done that before you started, you now have to do your regression all over again. But you've got your data listed. So you go back to stat, you go to calc, you go down to quadratic regression 5. No, we're now doing this equation. I'm just using a different calculator. I have my data in L1 and L2. I go to my store regression equation. I hit my vars variable, go over to my y variable, hit enter and put it in y1, go down and calculate this baby. And there's all my information. Same exact set of A, B, and now in this case it's C because I have three terms. I have a quadratic versus a linear. So the first thing I do is I write in my equation. It's negative 0.00482 x squared plus 0.37992 x plus 2.8662. There's my quadratic regression. My R square value is even better, believe it or not, than my regression R square, 0.9859. Okay. So if you look at this next page in your lecture notes, it says selecting a model. It's the last thing in your lecture notes. At the beginning of the modeling process, we must decide whether a linear, quadratic, cubic, blah, 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 which of these is suitable for modeling a situation. There's no exact answer, folks. Here are some criteria or guidelines for selecting a model. Here we have two choices. They're both going to be pretty good. Look at your R square values. The graph of the model should fit the points well. They both fit very well. Use the simplest model that captures the pattern of the data. I'm going to come back to that. The model should make sense within the context of real-world situations. So here we go. If we look at our pictures here, if we do zoom 9, there's the quadratic. And if we look at zoom 9 here, there's the linear. Okay? Both of these models fit the data pretty well. Don't you agree? In fact, the quadratic fits it even a little bit better than the linear model. So what's a Math 107 student to do? Which one do you choose? Why would you choose? Would you feel confident about either one of them, Fabian? Yeah. Okay, I'm just going to fill in this next little part in your lecture notes. I'm going to just fill in right here your confidence level. So you'd be confident, yes, very confident for both of them. But I think, Fabian, after reading through those few criteria, you're going to be choosing one of these over the other. And what's your rationale for doing that, Fabian? You're going to choose a quadratic, and why is that? Closer to the points. And it says, what may make sense in the context of the real world situation? What does our end behavior for our, now remember, this only goes to 2000. So if I keep following this linear model, and we're out here now at 2015, which is way up here, it's saying that the number of women in the workforce is continuing to increase at about the same rate. That's what the line's going to tell you, whatever that slope was. I think it was 0.211, right? This one, what's this one telling you? Well, it's increasing a little bit. It might increase a little more, okay? But then it's actually going to start to what? Decrease, because your leading coefficient is negative. Now, in the long run, it's not going to be a good model because it's going to go down to negative numbers of women. But what do we do for 2011? Let's look. How do we predict the number of people in the workforce for 2011? All right, so first of all, we have to take our models and we have to figure out what's the value for X here for the year 2011. 41, how'd you get 41? Yeah, the number of years after 1970. 1970 is our base year. So we got 41. So all you do is plug 41 in wherever you see X. But guess what? You don't have to work that hard, folks, because your calculator is going to do it all for you. You already got these equations right in your calculator, so use your calculator. Go up to table set, put in 41. There you go. Table set, put in 41. That's the year you're interested in. And then just go to your table. Go to your table. So with the model for quadratic regression, it's predicting 10.333 million. The model for, oh, I didn't put in 41. I put in 14 by accident. Oh, that's 41. Oh, it's because it's ask. I wanted to do it automatically. So let's hit that. Second table. Okay. So it's with the linear model, it says there's going to be about 12.6 million. Okay, so they're different. They're definitely different. As you can see, that our quadratic model is still increasing, and it looks like around 41 we've maybe hit our maximum point. Maybe I don't see the data before that. So you put in both of these values, all right? And I think based on everything that I've read, 10.333 million. The packets that I've just received, which had data, what was it, 12 point what? 12 point something. Oh, that's linear. Where's my quadratic? Nobody wrote it down, huh? 12.646. Okay, 12.646. All right, million. So again, as long as you can provide a rationale for either one of these, okay, models, as Fabian said, he would pick the quadratic. It looked like a closer fit, but in the long run, for at least from 2000 to where we are today, it's probably a more accurate picture. Now, the end behavior is what we're talking about here. The end behavior for each model, for your linear model, as X gets bigger and bigger, your number of women is going to increase without bound. That's certainly not going to happen. And also, with your quadratic, eventually you're going to have model breakdown because you're going to get a negative. So we have to just make our best choice based on what you know about your data set, what you think might be realistic. And in this case, to go a little bit beyond 2000, I would probably use the quadratic model. And the two articles I received from the librarian last night supports that the actual number of women is slowly starting to decrease, the percentage of women with children under the age of 6. Okay, and does anybody know what worldwide phenomenon actually got so many women into the workforce initially? Anybody ever see, huh? Well, I'm not telling you the year. I'm just wondering. World War II, right. That's when we had so many of our men go off to war that women went into the workforce and filled the places of men. Rosie the Riveter, right. That's what I mentioned in my first class. So these are the things that I want you to consider as you work through the data sets in your class activities. Please write down on class activity number 1 when it says to find the vertex of the parabola, say, ask Linda how to do this on the calculator, because I want to show you how to do it on the calculator. Have fun with the data sets. I would suggest looking over all the data sets. Start with the data sets that interest you the most. You don't always have to start with number 1.